Hello, my name is Frank. So in this special package, we are going to look at the Laplace transform. And before we start, we have to know what the Laplace transform is all about. So we are taking the definition. Let f of x denote any expression in x defined for x greater than or equal 0. The Laplace transform of f of x denoted by this symbol now is Laplace transform of f of x is defined as Laplace transform of f of x is equal integral from infinity to 0 of exponential minus sx f of x dx. Now, the value of s is a variable. S is a variable, and the value is so choosing such that the semi-infinite integral converge. Now, we also know that s is greater than 0 for s greater than 0, because if s is less than 0, as exponential minus s approaches infinity and s approaches infinity, you see that the semi-integral will diverge. The semi-infinite integral will diverge, will not converge. And I believe we have done convergence of series. So we know what we mean by divergence and convergence, when a series converge and when a series diverge. So we define the Laplace transform in this way, so that if we look at the Laplace transform of a constant, let's start there. That is the Laplace transform of a constant Now, let A be any constant the Laplace transform of A denoted by is defined as Laplace transform of A is integral from infinity to 0 exponential minus sx a dx. So if I have that, then if I integrate here, we know that I will have a, A is a constant, bringing A out, I will have from infinity to 0, exponential minus sx, the x. Of course, if we integrate here, we'll have, we integrate here, we have exponential minus sx all over minus s. Yes, all over minus s. This place come down. Now, we have that from infinity to 0. We are going to put that. Now, if we put infinity in the place of x, we'll have that everything there is a times 0. Everything will be 0 for infinity. Because when here is 0, 0 divided by minus s is 0. Then minus the downside. Minus. Of course, if we put here 0, 0 times 0, we have exponential 0, which is 1. So we have minus 1 all over minus s. Of course, if we do that, minus can cancel minus, so that we have a plus 1 all over s. Now, this times 0, a times 0 is 0. Then a times 1 will give us a all over s. S is greater than 0. So that the Laplace transform of any constants will be a all over s. Okay. It depends on the variable that I'm using here. Some people will use whichever variable that you like in this place. So it will be the constant all over the variable that you are using. Okay. That is the Laplace transform of a constant. So let's also look at the Laplace transform. Laplace transform of exponential ax. Don't forget that a is any constant, but the Laplace transform of exponential ax. What would be this Laplace transform? The Laplace transform of this will be defined to be integral from infinity to 0, exponential minus sx times exponential ax dx. And if that happens, we see that I can integrate this in this way. Integral from infinity to 0, exponential minus sx times, okay, look at this. So I can write this as minus s minus a x. You see, this times this, and x will give me this. This time this will give me plus. So by the time this times it will have this back. So I now have the x. Now if I integrate this, we will have exponential minus s minus a x all over minus s minus a. That's what we will have. Then at infinity to 0, you can then have, if I have infinity here, if I put infinity, everything there becomes 0. You have 0 minus, then if I put 0, then here will be 1. So you have minus 1 all over minus s minus a. Okay. So that means this and this can go. So I will have 1 all over s minus a. S minus a is greater than 0. So this is the Laplace transform of exponential a. So that if I have maybe exponential 2x, exponential 2x, then if I take the Laplace transform of exponential 2x, then it will give me 1 all over s minus 2. That becomes the Laplace transform. So we are using all these words. We are going to see the application to differential equation, how you use it to solve differential equation. It's very, very important to know it. So we start from the scratch so that you understand the process. So let's look at the Laplace transform of exponential minus ax. So let f of x is equal exponential minus ax. So the Laplace transform of f of x, of course, will be equal to the Laplace transform of exponential ax, which is integral from infinity to 0 exponential minus sx times exponential minus ax dx. So that this will give us integral from infinity to 0 exponential minus s plus ax dx. You see what I'm doing here is, since the bases are equal, take 1. So I add the power. Of course, if I use this to times this, and I use this to put here, we'll get back minus a. Now if I integrate this, I will have, integrating this, I will have exponential minus s plus ax all over minus s plus a. That is what I will have. So that if I put this value, we will have, you see, when infinity enters here, we have 0 minus, okay. Then when we put 0, so here we have 1. So you have 1 all over minus s plus a. So this can cancel this. So we have 1 all over s plus a. So s plus a is greater than 0. So therefore, the Laplace transform of minus ax is equal 1 all over s plus a, which implies that if I have a Laplace transform of exponential, say 3x, exponential minus 3x, so it will be what? It will be 1 all over s plus 3. That is the Laplace transform. So it's very simple. We want to look at Laplace transform of x exponential minus ax. The Laplace transform of x exponential minus ax will be equal to integral from infinity to 0 exponential minus x times x exponential minus ax dx. No, that is what we define it. So, and then this will give me integral from infinity to 0 exponential minus sx times okay, let me take x first so that we can join these two. So we have exponential minus s, okay, plus ax. You see what I'm doing here? Taking this one x, so this and this can be joined, the x. Now this is integration by parts. This is integration by parts. So we know that u is equal x, and that the v is equal exponential minus s plus ax. So that v, if you integrate this, you have v, and then you have v will be equal exponential minus s plus ax all over minus s plus a. That will be v. Now, using the formula for integration by parts, which we know to be that integral u dv will be equal uv minus integral v du. So what happened there is that we will have uv, of course u is x, so v is this, which is exponential minus s plus a x all over minus s plus a minus integral, look at this, integral, then we have v, so v again is exponential minus s plus a x all over minus s plus a du. Of course, du is the x. So we can now substitute the values, or let me break it again to have exponential minus s plus a all over minus s plus a plus, you know why? Because I'm bringing this out, so this will give me plus 1 all over s plus a. That is what this place means by bringing it out. Now, of course, okay, if I bring it out, I'll have that. So integral minus s plus a x. Yes, the x. Okay, we are not going to put value first, but we integrate this. You have to integrate this. So I brought this one out. If I bring it in, it will become this. So bring it out, this minus cancel minus, we have plus. Now, I want to integrate here. Then I will have x exponential minus s plus a x all over minus s plus a plus 1 all over s plus a. Then if you integrate this, of course, we will have exponential minus s plus a x all over minus s plus a. Okay, so that is what we will have. Now, we want to now put the value, and because of that, I want to put it in a way that we will understand. So I want to break it into two parts. If we put this way, you see that putting infinity will have 0. Even putting this 0, you have 0 because of x. So everything there becomes 0 plus, now look at that. Now putting infinity for here, we will have 0, yes, because it will be 0 for infinity here. So everything times here is 0. Minus putting 0 there. So we have minus 1. Yes, minus 1. But don't forget that there is something outside here. There's something else. So if here is 0, then it will have plus before this one, s plus a. So that this side, putting here, we can get 0 minus, then putting 0 here. We'll have 1, because anything less to 0 is 1, so exponential 0. 1 minus s plus a. Of course, this can cancel this. So what we have here is 1 all over s plus a, then we have plus 1 all over s plus a. That is what we have. And by the time you times this, you have 1 all over s plus a squared. That is what it means. So, therefore, the Laplace transform of x exponential minus ax is equal 1 all over s plus a. So that is the plus a squared. So that is the Laplace transform. Now, we insist that s plus a is greater than 0. So, this is how we define the Laplace transform. It's simple. Next one we'll look at is the inverse transform. Now, we define that the Laplace transform of f of x, look at. We know that the Laplace transform of f of x denoted by f of x is defined as integral from infinity to 0 exponential minus sx f of x dx. Now, the Laplace transform is a variable, is expression in the variable s. It's expression in the variable s, which Laplace transform of f of x is equal f of s. So now, the Laplace transform is an expression in the variable s such that f of x is equal f of x, which is equal Laplace transform of f of x. So what it means is that if f of x is equal to f of s, then f of x is the inverse transform of f of x. And then we can write it that the inverse transform, look at the inverse transform, yes, the inverse transform of f of s will be equal f of x. So that is what it means. The Laplace transform is such that, see, the inverse, since s is the expression in s, such that Laplace transform of f of x is equal to f of s. Because this is the Laplace transform of f of x. It is also equal to this. So now if this is equal to this, then this is the inverse of this. So when we take this, we have the inverse transform. Now let's see how we apply the inverse transform. We are looking at these examples so we can apply the inverse transform. To find the inverse transform of the following functions. Number one, we have f of s is equal 1 all over s plus 2. So now we see that the inverse of f of s will be what? We recognize this when we try to prove this. So this will be equal to exponential minus 2x. That is just that. Because if you take the Laplace transform of this, it will give you this. Then the inverse of this is coming back to what gave you this. So it's just very simple as that. Now let's pick number 2. F of s is equal 1 over s minus 2. So the inverse transform of f of s will be equal exponential 2x. Yes, exponential 2x. Now for number 3, we have that f of s is equal 4 over s. Of course, this will imply that the inverse transform of f of s will be equal 4. Because we know that if we take the Laplace transform of this, we will have 4 over s. So the inverse is that. It's very simple. So the next one we look at is the Laplace transform of the derivative. The Laplace transform of derivative. You know, we say that if f of x is any function or any expression, that the Laplace transform of f of x, which is denoted by this, is equal to, is defined as integral from infinity to 0 exponential minus sx f of x dx. So now, if we need the Laplace transform of a derivative, that means f prime of x, then it will be the same as integral from infinity to 0 exponential minus sx times f prime of x dx. And if we have this, we know that by integration by parts, that we can integrate this. So let's see how we'll go about it. So we know that by integration by parts, integral u dv is equal uv minus integral v du. Okay. Now, what it means is that in this place, this is u and this is the v. So that when we integrate here, we have v. So applying that, we'll have u, which is exponential minus sx v. V now is f of x. You know, this is f prime of x. So integrating, I'll have f of x. All right. Minus integral v. Okay, v is f of x. And du is, see, we have u is equal exponential minus sx. So that du all over the x will be minus s exponential minus sx. Okay, now you see that du is equal minus s, look at that, exponential minus sx dx. So this is what we put in the place of du. So du is minus s exponential minus sx dx. And so if that happens, we can have it in this way, that exponential minus sx f of x, bringing out this constant s, this s here, bring it out now, plus s integral exponential minus sx f of x dx. Okay. Now what happened is that, like what we have seen now, we see that this could be written as exponential minus sx f of x plus s. This one, by our definition, we say that the Laplace transform, look at the Laplace transform of f of x is equal to f of s. That is what we said, f of s, and which is the same as f of x. Now, if you look at this place, when we define f of x, we said that the Laplace transform of f of x is equal to exponential minus ss times f of x. So what it means here is that this one is f of x. The whole of this is the Laplace transform of f of x, which is also equal to f of x. So I can just put f of x in that place. Okay. Now, if I put that, taking here, because these are variables that we putting infinity to 0, I will have putting infinity here. Everything here will give me 0. Now, if I put 0, so we'll have minus f of 0. Because if I put 0 here, definitely I will have 1. Then if I put 0 here, I have f of 0. 1 times f of 0 will give me f of 0. Plus, if you go this way, you have f of s. So this, I can write this as s f of s minus f of o. So this is the Laplace transform of the derivative. It's given by this s of f s minus f of o. Let's also look at the Laplace transform of higher derivative. Higher derivative such as, like, let's say the second order. So if I take the Laplace transform of the second order, that is f prime of x, in this same definition, it will give us s squared f of s minus f of o minus f prime of o. Okay, so this place, and this is s f of o, s f of o. So let's pick example. Now we have to solve each of the following using Laplace transform method. dy dx minus y is equal to d square y all over the x squared plus 5 dy dx plus 6y minus 2 exponential minus x. Okay, that is equal 2 exponential minus x. Now let's pick the solution and see how we can apply the Laplace transform. We start from 1. So we have that dy dx minus y is equal to, okay, there is condition that f of o is equal 0. Now in this one, f of o will be equal f prime of o, which is 0, because the condition will allow us to solve. Now this is what we have, and we know that dy dx is the same thing as f prime of x. So the Laplace transform of f prime of x is s f of s minus f of o, then minus, look at this, f of x. You know why is f of x, and for f of x we have f of s. We will also take the Laplace transform of this, which is what? Which is 2 all over s. Look at that. See, what we are doing here is this. We take the Laplace transform of this. We take the Laplace transform of this and this. So that means what we are doing here is Laplace transform of f of x minus Laplace transform of, okay, f prime of x of f of x is equal to Laplace transform of 2. See that? We are taking the Laplace transform of all of them. So we have this. Now if you do that, we know that this place from condition is 0. F of 0 is 0. So it means that everything here will go. So we have s f of s minus f of s is equal to all over s. Now we want to factor out this. To factor out something here. We do that, we will have that f of s minus 1 will be equal to all over s. So that f of s will be equal to all over s minus 1. You know, when we divide this and times it by here, we'll have this. Alright, but we recognize this as partial fraction. So we can resolve it to partial fraction to have 2s minus 1. You know, we are going to assume a partial fraction of this form a plus b all over s, okay, all over s minus 1. It is assumed that the students, they have studied partial fraction very well in first course mathematics. So if you know that you are not too familiar with partial fraction, we have a package for that which you can lay hands and you get everything about partial fraction is well simplified. Now, if we do this, we now see that this can be the same as 2 all over s minus 1 will be the same as you know, if I want to take LCM of this, I will have something like this. So that this going here, s can cancel s, so I have a times s minus 1. Now, this way, here can cancel, so I have plus ds. So, as it is now, you see that here and here they are the same identity. So I can say that 2 is the same. It's identical to a s minus 1 plus ds. By our cover-up method, if we put s is equal 1, so that we can get 0 here, we will have that b is equal to. Now put s is equal 0, so that we can remove this. So if that happens, we will have that a is equal minus 2, is it not? So when here is 0, so minus 1 times here is minus a, so a is minus 2. Okay, that means that here is the same as writing that 2 all over s minus 1 is the same as minus 2 all over s plus 2 because b is 2 all over s minus 1. Okay, so what we do now, we have got this. So what we do is to take the Laplace transform of this, the inverse transform. Sorry, to take the inverse transform. So taking inverse transform of the right hand side, of course, because we have resolved this to this. So this is the same as this. We'll have the inverse transform of minus 2 all over s plus the inverse transform of 2 all over s minus 1, and that will give us, if our inverse transform of this will give us what? Minus 2, yes, minus 2, look at that, minus 2, because if we take this minus of, we see that 2 over s will give us a constant 2, plus, then this will give us 2, now look at this, if we shift these 2 out, you have 1 all over s minus 1, which is, if we take the inverse, we have exponential x. So we have exponential x. Or we can write it like this, that 2 exponential x minus 2, which implies that the Laplace transform of this is the same as 2 exponential x minus 1. Yes, 2 exponential x minus 1. So we are able to solve the differential equation as it is. We are able to have a solution of the differential equation, which is 2 exponential x minus 2. So the next one is solution number 2. We have that d square y all over the x squared plus 5 dy all over the x plus 6y is equal to exponential minus x. Alright, so now let me write this in a way that we will understand. You see, f prime prime of x plus 5 f prime of x plus 6 f of x is equal to exponential minus x. Now this is the second order derivative, and from what we have seen, the Laplace transform, we will take the Laplace transform of all of them. Laplace transform of f prime prime of x plus also take 5. Then we have the Laplace transform of f prime of x, because the Laplace transform multiplied by a constant is the same thing as the constant multiplied by the Laplace transform. So that is one of the properties that Laplace transform has. Now plus 6, we take the Laplace transform of f of x. Then we have this, the Laplace transform of 2 exponential minus x. We are taking Laplace transform all of them. Now, what is the Laplace transform of second order? Is s squared f of s minus s f of o minus f prime of o, then we reach here plus 5. Now this is 5, not s, this is 5. So we now take the Laplace transform of this one, first order, which we know to be s f of s, this is with s. Note this, that this one is s, while this is 5, minus f of o, okay. So that here we take the Laplace transform of this, which we will have to be, okay, let me use this, 6, we have plus 6, we take the Laplace transform of f of x, you have f of s. So it's equal the Laplace transform of this, and that will give us 2 all over s plus 1, because this is minus 1, so s plus 1. That's what we have. Alright. Now the condition was that f of o is equal f prime of o, which is equal 0. So that means this particular one will go, because we have to do this s of o minus f prime of o plus 5s f of s minus 5f of o plus 6f of s. Then we have 2 all over s plus 1. Now, if we apply the condition, you see that this will go. Even this place will go. And even this will go. So, what we have is s squared f of s plus 5 s, okay, f of s plus 6 f of s is equal to all over s plus 1. Now, if we factor out f of s, we will have s squared, look at that, we have s squared plus 5s plus 6 is equal to all over s plus 1. Now, we know this to be quadratic. So, f of s will be equal to all over s plus 1 times this one. So, this is quadratic, but if you resolve it, you know, this one is 5s, this is 6. So, 2 numbers to get 5, and when you times it, you get 6. Will be to be s plus 2, s plus 3. By quadratic, you know, if you solve this, you have this. So, this is how it is. And if we have something like this, we can then resolve it into partial fraction, where we know that 2s plus 1, s plus 2, s plus 3, will assume a partial fraction. Partial fractions of the form A is equal s plus 1 plus b is equal s plus 2 plus c is equal s plus 3. You know that we have different denominators, different factors. So if we do that, then 2 will be equal, you see, to a s plus 2. That's why I said you must be familiar with partial fraction. So 2 will be a times this and this. So s plus 3 plus b, s plus 1, s plus 3 plus c For C, we will have s plus 1, s plus 2. Okay. Now, if we have that, okay, let me use here. I have to put s is equal minus 2, so that here can be 0. And if I put that, see, the whole of this place will be 0, and the whole of here will be 0. So that means we will be able to find b. So that means 2 will be equal b minus 2 plus 1, and then minus 2 plus 3. Of course, 2 will be equal minus b. Okay, look at that. b minus 1. And this one will be what? 1. So that implies that b, here will be minus b. So they mean that b is equal minus 2. We have got b. So the next thing now that we'll get is to put s is equal, if we have made this one, the next one will be minus 1. Let's put minus 1. S is equal minus 1. Then we'll have 2 will be equal. Now, if I put minus 1 here, then minus 1 here, so the whole of this is 0. See, I will have that 2 is equal a minus 1 plus 2 minus 1 plus 3. That will give me, see, it will give me a 1, and this is 2. So what do we have? We have 2a, because every time this you have, this implies that 2 is equal to a. Therefore, a is equal 2 over 2, which is 1. A is 1. Then, the next thing I will do is to put s is equal minus 3, because I want to get the value of c. So if I put minus 3, see, the whole of this will go. The whole of this will go. So what remains is this. You can get c now. So 2 is equal minus 3 plus 1 minus 3 plus 2. So we'll have that 2 is equal this. Will give me, okay, c. Let's see here. So this will give me that c is minus 2 times, c times minus 2 because of minus 3 plus 1. And then this is minus 3 plus 2. So I have minus 1. Alright. If we times this and this, we'll have that 2 is equal 2c, which implies that c is equal to divided by 2, which is 1. So we have therefore 2 all over. Okay, let's start from a, this place, so that we can finish it one time. Therefore, a all over s plus 1 plus b all over s plus 2 plus c all over s plus 3 is the same as writing, a is 1 all over s plus 1. Then b is minus 2 minus 2 all over s plus 2. Then c is 1 all over s plus 3. Okay. So the next thing we'll do now is to take the inverse transform of these functions. That's what we'll do now. So taking the inverse, we have the inverse transform of this, which is 1 all over s plus 1 plus the inverse transform of minus 2 all over s plus 2 plus the inverse transform of 1 all over s plus 3. Now if I take this, of course we know this, the inverse transform of this will give us exponential minus x. Okay, now taking the inverse transform of this, we have minus 2 exponential minus 2x from what we have done in the inverse transform. So we come to this place, we have plus exponential minus 3x. Yes, so we have this. So therefore, y is equal to this. We were given the function in terms of y, not f of x. So y is equal to this. So we can use Laplace transform in that way to solve a differential equation. You see, we will end here, but I like to get another package for power series solution of differential equation. It's very interesting. So that you equip yourself very well with all these lectures. So thank you very much, and we urge you to take your studies very, very serious. Very, very serious. So we have a lot of packages that you can call for that will help you in your mathematics courses. We have partial derivatives, we have complex variable, we have lectures on complex variable, we have abstract algebra, all those ones. So if you want it, you just call the number on your screen, it will get to you wherever you are. So thank you very much.